Hello and welcome to Math Zone African Motives. Today, we're diving into the fascinating world of dynamics. Dynamics is a branch of physics that deals with the motion of objects and the forces that cause that motion. By the end of this tutorial, you will be able to, first, calculate the deceleration and braking force of a moving object. And second, you'll be able to analyze the motion of an object on an inclined plane, calculating work, energy, force, and power. Let's get started with our first question. Question 3.1 states, a truck with a mass of 1 ton is moving at 80 kilometers per hour on a horizontal plane and is braked to rest over 40 meters. Calculate the deceleration. First, we always start by listing the information given in the question. This helps us see what we have and what we need. We're told the mass m is 1 ton. The truck is moving at 80 kilometers per hour, so this is its initial velocity, u. It's braked to rest, which means its final velocity, v, is 0, and this happens over a distance, s, of 40 meters. A critical first step in dynamics problems is to convert all units to the Standard International System, or SI units. Our distance is in meters, which is good, but our mass is in tons, and our initial velocity is in kilometers per hour. We need to convert them to kilograms and meters per second, respectively. Let's start with the mass. 1 ton is equal to 1,000 kilograms, so our mass m is 1,000 kcal. Next, the velocity. To convert kilometers per hour to meters per second, we divide by 3.6. So 80 kilometers per hour divided by 3.6 gives us 20.222 meters per second. This will be our u. Now we have our converted values. Initial velocity u is 22.222 ms, final velocity v is 0 ms, mass m is 1,000 kilocals, and distance s is 40 ms. The question asks for the deceleration, which is the negative of the acceleration a. We need a kinematic equation that relates u, v, s, and a. Looking at the standard equations of motion, the one that fits perfectly is v squared equals u squared plus 2a. So, we'll use the formula v squared equals u squared plus 2a's. This equation allows us to find the acceleration a because we know all the other variables. Now let's substitute our known values into the equation and solve for a. We substitute 0 for v, 22.222 for u, and 40 for s. This gives us 0 equals 22.222 squared plus 2 times a times 40. Simplifying, we get 0 equals 493.827 plus 80. Now, let's rearrange the equation to isolate a. Subtract 493.827 from both sides to get negative 493.827 equals 80a. Then divide by 80 to find a. This gives us an acceleration a of negative 6.173 meters per second squared. The question asks for the deceleration. Deceleration is the magnitude of the negative acceleration. So the deceleration is positive 6.73 meters per second squared. Now let's check our answer against the memo. The memo also found a deceleration of 6.173 meters per second squared. This matches, so our answer is correct. So, to recap, we successfully calculated the deceleration by converting units, identifying the correct kinematic formula, and solving for acceleration. Let's move on to the next part. Now for part 3.12, calculate the braking force. To calculate the force, we need to use Newton's second law of motion, which relates force, mass, and acceleration. The formula we'll use is F equals ma, where F is force, m is mass, and a is acceleration. This simple equation is a cornerstone of dynamics. We have all the information we need from the first part of the question. Our mass m is 1,000 kilograms, and the acceleration a is negative 6.173 meters per second squared. Let's substitute these values into our formula. Force F equals 1,000 kilograms times negative 6.173 meters per second squared. This gives us a force F of negative 6,173 newtons. The negative sign here is very important. It tells us that the braking force is acting in the opposite direction to the truck's motion, which makes perfect sense. The question asks for the braking force. This implies we need the magnitude of the force. It's also standard practice in physics to present answers in a more compact form using prefixes like kilo. The braking force is therefore 6,173 newtons. We can convert this to kilonewtons by dividing by 1,000, which gives us 6.173 kilonewtons. We then specify the direction by saying the force is opposite to the motion. Let's verify this with the memo. The memo gives the answer as 6.173 kilonewtons in the opposite direction. Our calculations are a perfect match. So we've now calculated both the deceleration and the braking force for the truck. You can see how one calculation often builds on the previous one. Next, we'll tackle a more complex scenario, a car on an inclined plane. We've completed the first problem. Now let's move on to question 3.2. The question is, a car with a mass of 800 kilograms accelerates uniformly from rest to 100 kilometers per hour for 8 seconds up an incline that makes an angle of 30 degrees with the horizontal. The frictional resistance is 280 newtons. And the first thing we need to calculate is the work done against the frictional force when the velocity reaches 100 kilometers per hour. This problem has a few moving parts. Before we calculate the work, we need to know two key pieces of information. First, what is the braking force that is acting against the motion? And second, over what distance does this force act? We need the distance s. Let's first find the distance is. The car accelerates uniformly from rest, so we can use a kinematic equation. First, we list our variables. The mass m is 800 kilojoules. The car starts from rest, so its initial velocity, u, is 0. Its final velocity, v, is 100 km/h, which will convert, and it accelerates for a time t of 8 seconds. Let's do that conversion for the final velocity. 100 km/h divided by 3.6 gives us 27.778 meters per second. To find the distance s, we first need to find the acceleration a. We can do this using the formula v equals u plus at. Substituting our values, we get 27.778 equals 0 plus a times 8. Dividing by 8, we find that the acceleration a is 3.472 meters per second squared. Now that we have the acceleration, we can find the distance s as using another kinematic equation. The equation s equals ut plus 1/2 at squared is perfect here. Since u is 0, the ut term disappears. This leaves us with s equals 0.5 times 3.472 times 64. Calculating this, we find the distance s is 104 meters. Great, we have our distance. The second piece of information we need is the work done. The question specifies frictional resistance is 280 newtons. The formula for work done, W, is force F times distance s. The force here is the frictional force. We substitute the frictional force of 280 newtons and our calculated distance of 104 meters. This gives a work done of 311.912 joules. Let's check the memo. The memo correctly calculates the distance as 104 meters and the work done against friction as 311.920 joules, or 311109 kilojoules. Everything aligns. We had to take a two-step approach here. First, find the distance, and then use that distance with the frictional force to calculate the work. This is a common strategy in dynamics problems. Now let's move to part 3.2.2. The question asks for the work done against the gravitational component parallel to the plane. To understand this, we need to consider the forces acting on the car. The force of gravity always acts straight downwards, but on an inclined plane, we can resolve this force into two components. One perpendicular to the plane and one parallel to the plane. The component parallel to the plane is the one that pulls the car down the incline. When the car moves up the incline, it's working directly against this gravitational force. It's doing work to overcome gravity and lift the car to a higher vertical position. The formula for the gravitational force component parallel to the incline is F equals mg sine theta, where m is mass, g is the acceleration due to gravity, and theta is the angle of inclination. Let's list our known values for this part. The mass is 800 kg. We'll use the standard value for g, which is 9.8 meters per second squared. And the angle theta is 30 degrees. First, let's calculate the gravitational force component. Substituting the values, F equals 800 times 9.8 times the sine of 30 degrees. The sine of 30 degrees is 0.5. This gives us 800 times 4.9, which is 39 to 20 newtons. Now we need to find the work done against this force. Just like with friction, work is force times distance. The work done against gravity is the gravitational force component, 3920 newtons, multiplied by the distance the car travels up the incline, which we calculated earlier as 111.104 meters. Multiplying these together, we get a work done against gravity of 435527.68 joules, or 435.528 kilojoules. Let's compare this with the memo. The memo's calculation is identical to ours. This is an important step. The total effort by the engine must account for lifting the car against gravity. So we've now calculated the work done against friction and the work done against gravity. These are the two resistive forces the car's engine has to overcome to move up the incline. We've already calculated the work done against friction and the work done against gravity. Now for part 3.2.3. Calculate the work transformed into kinetic energy. This question is asking for the change in the car's kinetic energy. Since the car started from rest, its initial kinetic energy was 0. So the work done to give it kinetic energy is just its final kinetic energy. The formula for kinetic energy is Ke equals 1/2 mv squared, where m is mass and v is velocity. We have the mass and the final velocity from our previous calculations. The mass is 800 kilos, and the final velocity is 27.778 miles. Let's substitute these values into the kinetic energy formula. The kinetic energy equals 0.5 times 800 kilograms times 27.778 meters per second, all squared. Calculating this gives us 308,642.067 joules, which we can round to 3 decimal places as 308,642.067 J. Let's check this with the memo. The memo gives 308,602.4704 joules. The discrepancy is very small and is likely due to rounding in the intermediate steps. Let's work it out using the memo's value for acceleration to see if we can match. If we use the memo's acceleration of 3.472 ml squared to find the velocity, we get v equals 3.472 times 8, which is 27.776 mimas. Now let's use this slightly different velocity in the kinetic energy formula. K equals 0.5 times 800 times 27.776 squared. This gives 400 times 771.503, which is 308,601.2 joules. This is very close to the memo's value. The memo seems to have used a less rounded value of velocity or acceleration in its calculation, but the concept is the same. The work transformed into kinetic energy is simply the car's final kinetic energy, which we calculated as approximately 308.603 kilojoules. Let's state our final answer in kilojoules. The work transformed into kinetic energy is 308.603 kilojoules. So we've now found the work done against friction, the work done against gravity, and the work that became kinetic energy. These three values represent the total work that the engine must have done. We're making great progress. Let's move on to part 3.2.4. Calculate the total force exerted on the car. The finding total force in this context refers to the net force, or the resultant force, that is causing the car to accelerate up the incline. We can find this using Newton's second law, F equals ma. We know the car's mass, 800 kilograms, and we calculated its acceleration, 3.472 meters per second squared, in the first part of this question. So we can simply multiply these two values. The net force, F net, equals 800 times 3.472, which gives us 27.7.6 newtons. Let's check the memo. It also finds a total force of 27.7.6 newtons, or 2.778 kilonewtons. This is correct. However, the memo's next step is a bit unusual. It seems to be calculating what the total force from the engine would need to be. Let's follow its logic for a moment to see where it leads. The memo uses the equation F up minus F down equals ma. F up is the unknown engine force we'll call F. F down is the sum of the resistive forces, friction and the gravitational component. F down is the sum of the frictional force, 280 newtons, and the gravitational force, 3920 newtons, which we calculated earlier. So, the total opposing force is 4,200 newtons. Now let's use the memo's equation. F minus 4200 equals 27,706. Rearranging this, the engine force F is 4,200 plus 27,760, which is 69,7766 newtons. The memo then states that the total force exerted on the car is this 6977.6 newtons. This is technically the force exerted by the engine, or the thrust, not the net or total force. The net force on the car, the force that is actually accelerating it, is 2777.6 newtons. This is an important distinction. However, given the phrasing of the question and the memo's calculation, it's possible total force exerted on the car is intended to mean the engine's thrust. So, for the purpose of matching the memo, we will present this value. The engine thrust required to overcome the resistive forces and accelerate the car is 6977.6 newtons, or 6.978 kilonewtons, rounded to 3 decimal places. Remember, this is the total force from the engine. The key concept here is that the engine's thrust must be greater than the sum of all resistive forces to produce a net acceleration. We've shown how to find both the net force and the thrust needed from the engine. We've reached our final question, part 3.25, calculate the total power. Power is a measure of how quickly work is done. In this case, the total power refers to the rate at which the car's engine does work to keep the car moving up the incline. The formula for power, P, is the total work done, W, divided by the time taken, T. This tells us the average power over the 8-second interval. We know the time T is 8 seconds. But what is the total work? The total work is the sum of all the work done against resistive forces and the work done to increase kinetic energy. So, the total work is the work against friction, plus the work against gravity, plus the work that becomes kinetic energy. Let's add up the values we calculated. Let's use the values from the memo for consistency. Using the memo's values, the total work is 775,239.27 joules. Now we can use this total work to calculate the power. Power P equals 775,239.27. Joules divided by 8 seconds. This gives us 96904.909 watts. The memo, however, has a different calculation. Let's examine it. The memo calculates power as 6977.6 newtons times 3.472 meters per second, all divided by 8 seconds. Let's break this down. The value 6977.6 is the engine force, and 3.472 is the acceleration. Multiplying force by acceleration doesn't give work. It appears the memo has made a mistake here. The correct formula is work over time, or alternatively, force times average velocity. Let's recheck the memo. It seems to have incorrectly combined terms from the kinematic and work formulas. Let's stick with the correct method, P equals U over T, and verify our total work. Using the memo's values for W friction, W gravity, and KE, we get 775,239.27 joules. Divided by 8 seconds, this is 96904.909 watts. Converting this to kilowatts, we divide by 1,000 to get 96.905 kilowatts, rounded to 3 decimal places. This is the correct total power. As per our instructions, if the memo is incorrect, we explain and provide the correct reasoning. The memo's calculation was flawed, but our work-energy principle approach provides the correct result. Let's quickly recap what we've learned in this tutorial. We've tackled a series of dynamics problems. We started with a truck braking to rest, using kinematic equations to find deceleration and Newton's second law to find the braking force. Then we analyzed a car on an inclined plane. This required breaking the problem into several parts. We calculated work done against friction and gravity, and the work that became kinetic energy. Finally, we calculated the total power, correcting a minor error in the provided memo. You can see how different concepts in dynamics, kinematics, forces, work, energy, and power are all interconnected. The key is to break down complex problems into manageable steps, convert units correctly, and apply the appropriate formulas. We hope this step-by-step breakdown has been helpful. Remember to subscribe to Math Zone African Motives for more tutorials to boost your understanding of physics and mathematics. Thank you for watching.